Be 10 minutes ahead of time on the second floor. Don't come from the first floor. Go all of you upstairs to the second floor so that the TA can help you get seated. And please sit in the rows that they are empty. Don't take any seat you want. Just come in, fill every row. Don't skip any seat because this will be helpful for us when we're gonna give you the exam. So what do you need? You need a pencil. You need definitely pencils, eraser, and calculator. Definitely calculator. Bring your calculator with you and make sure that the batteries are working. Don't come here and, the battery is not working, I need a calculator. I can't have calculator for everybody in the class. Definitely bring your UMass ID. Please don't tell me, I forgot it in the car, it is in the parking lot, it's in the dorm, I don't know. Bring your UMass card. The TA gonna check your UMass ID to make sure that you're the person that is taking the exam. Bring your UMass ID. Come from the back door. Now, we don't have a class at 8 a.m., so don't come to the class tomorrow at 8 a.m. Now, I'm going to give you scan sheets like these, exactly like these. And what you're supposed to do is you're supposed to write your name in here and to bubble your name. Writing the name alone wouldn't help me because I'm going to pass them through scanner machines. The scanner machine. So if you don't bubble, I don't know your name. Okay? So bubble your name and make sure you're bubbling the right letters. The same for identification number. I don't want your birthday. I don't want the special code. Don't fill those. All what I need from you is to write down your identification card and an identification number, which is your UMass ID, and to bubble your UMass ID and bubble the right numbers of your UMass ID. Now, not everybody in the class is going to have the same exam. We're going to have three different exams. Now, how I'm going to figure out what exam you did? It's going to be, this is the first page of the exam. It's going to be information page. The second page is going to be the first page of the exam where it has the question. On the upper right side, there is the exam ID. So you take, let's say it is A. You put A in here. You don't put it in number 1. It's not the answer for question 1. It must be in here. If it is A, B, C, or D, you must write that on there. Okay, so the exam ID is not on the information page. It's the second page, right upper side. You're going to find your exam ID. So, to find your grade on OWL or in Moodle in a week or so, you need to do so. Failure to do so, first is gonna make your grade you're gonna take it after 2 weeks. Second, sometimes it will be, I don't know if that's really your scattering or not. I don't know if that's your exam or not. So make sure, please, once you get here, we directly gonna pass the scan for you so that you're like, calmly do that, finish it, then I'm gonna hand in the exam. So make sure 3 things: your name and bubble it, write your name and bubble it, your exam ID, write it on here, and the identification number, your UMass number, write it there. That's regarding the exam. The exam is a 27 multiple choice. Okay, your source, laptop. So it is a 27 multiple choice. You can have an hour to finish that. And I think that's it. Regarding the information page, I'm still getting emails. What exactly you're gonna give me in the exam? It's been for more than 4 weeks on Moodle under practice exams. It's called first page of the exam. It is exactly, I printed out from Moodle, and it is the first page of the exam. Now let's get going with the chapter 5. Again, I'm gonna be in my office for if you have any questions most of the day, except from 1:21, about 1:12 to 2:30, I'm gonna be out of my office. Then I'll be in my office till 4 p.m. If you have any question, you don't have to send me an email. Just walk in, and I'm in my office. I can answer your question. Okay, so we stopped. The last time we were talking, that was Friday. We were talking about thermodynamics, and we did talk about how to calculate the energy or the energy you need to heat something or to cool something. And we said that Q equals the mass times the specific heat capacity times delta T. And we did two examples. One example, we heated the water from 20. We had, I don't remember the mass of the water in that example, but it was a certain mass and of water. And we heated it up till from 20.5 to 98.5, my guess. Then we did exactly the second I clicker, the next slide, the second I clicker it was cooling this water from 98.5 to 20.5, and we find that the Q was exactly the same for both. It's the same amount of energy that is there. One was positive and one was negative. And we talked that, okay, we're gonna talk what does it mean that Q is positive or Q is negative when we calculate it. And that will bring us that if Q is positive, a positive Q, if Q is positive, we know that the specific heat capacity could never be negative. And the mass, we never heard about mass being negative. So delta T is the one that can be negative or positive. So if Q is positive, that implies that definitely delta T is positive. And if delta T is positive, that means T final minus T initial greater than 0. Therefore, T final is greater than T initial. In other words, when the system temperature increases, the Q is going to be positive. So when you heat the system, when you heat the water, when you heat something, when you take it from low temperature to high temperature, your Q must be positive. And that tells you that the water, when we heat the water, it is an endothermic reaction or a process. It is a process that needs heat to get going. Okay? So the energy has been transferred. That implies when the Q is positive, that implies the energy has been transferred to the object of study. In this case that we talked about is the water itself. The object absorbs the energy. So when Q is positive, it tells you that the system, the reaction, we're going to talk about reaction later on, but in here, the water needed heat to go to be heated, for example, from 20 to 98 or 95. Now, when Q is negative, and that doesn't mean that when Q is negative, the T final of the system of the water is less than the T initial. And that's when we have the water, we cool it down from 98.5 to 20.5. So the T final is less than T initial. So we cool the system. When we cool the system, the energy has been transferred from the object. So the object, we took energy from the object, from the water. So to cool it down to 20, we took energy from that, and this is why Q is negative. So any system that gives energy or we take energy from it, Q gonna be negative. For any system that needs energy, Q positive. So from now on, when you see Q positive, that's an implication that the system needs energy. You need to give it energy for the reaction to take place, for the process to take place. When you see that Q is negative, that means the system or the reaction releases energy during this process. You take energy from it during this process. Okay? Does that make sense? Cool. And that brings us to two other definitions, which are exothermic and endothermic reaction. So, an exothermic or system. In the exothermic reaction, the system gives heat, which is the example when we cooled the water, we took heat from it, so it released heat to the surrounding. Energy transferred from the system to the surrounding. And the system in here is the water itself, we call it the system. and the surrounding is anything other than the water. So, an exothermic reaction is the reaction that releases energy, that gives you energy. And definitely the Q of this is going to be negative. It's going to be Q minus. It's going to be in the minus. Now, an endothermic reaction, the system, which is the water, in this case, gains energy. We give it heat. We heat it up. We heat the water up to go from 20 to 98. So this reaction or this process is not really a reaction in this case, but later on we're going to begin talking about reaction that gives energy or take energy. So the reaction that needs energy, that needs some energy to get going, is called an endothermic reaction. And the energy of the system increases because I'm heating it up. Okay? So you need to keep in mind and to know those two terms, exo and endo. Exo is the reaction that gives energy or the process that gives energy, and endo is the system or the reaction that needs energy. Now, the first law of there is one of the laws of thermodynamics is the conservation of energy. That means energy can be neither destroyed nor created. It can be converted from one form to other, from one object to other, but it would never be lost. It wouldn't be I have energy and suddenly it disappears, or I don't have any fuel or anything and I have energy. That doesn't. Life doesn't go this way. There is a conservation of energy. The energy loss is going to be equal to the energy gain in any system. So, an example of that is, let's say I have a beaker. The beaker has 200 grams of water, and it is at 75. Then I have another beaker with 500 grams of water, and it is at 30. When I add those two together, when I add the water, which is at 75, and the one at 500 together, and I leave it for a little bit, then I put a thermometer in here, I'm going to find that the temperature in this 700, for this 700 gram, is one temperature. We're going to measure one temperature all over the beaker. It couldn't be two. We call this the final temperature. And this is at thermal equilibrium. And thermal equilibrium means when both are mixed well and all of the beaker has one temperature in there. And in this case, definitely the system is isolated. That means it's not losing heat to the surrounding. It's not a beaker, for example. It's not a cup of coffee in, for example, a glass, and it is losing heat. We're kind of isolating the system. We're going to find T final. 1 T for all the beaker. One temperature for all the beaker. Would this temperature be higher than 75? No. Very good. Would it be lower than 30? It's going to be something in between 75 and 30. And that brings us to the first law of thermodynamics, which is things when we put two stuff together, one is hotter than the other, one gonna lose heat to the other, and they both kind of equilibrate to a temperature between the two. And this, the reason behind that the Q gained plus the Q lost must be equal to zero. And here I'm talking about an isolated system, a system in a thermostat or something that we're not losing heat to the surrounding, to the whole room or thing. So the Q gain plus the Q loss must be equal to zero. This is the law of conservation. The energy can neither be created or destroyed. It can be converted from one object to the other, from one form, from kinetic to potential, from potential to kinetic, but we cannot lose it. We don't know, oh, I had energy, but I don't know where it is. It is a change to another form or to another object. So the Q gained plus Q lost equal to zero, and that applies to anything. It applies to a metal, for example, at 90 degrees, that I put it in a beaker that has water. At, for example, 25 degrees, it applies to anything. So applies to anything that one is more hot than the other, they're gonna kind of thermally equilibrate, and they're gonna have Q gained plus Q lost equal to 0. And here I'm gonna pause for a minute, and I want the attention of everybody in the class. Usually I give you this equation, and after the class, when all are online, you're doing, I have about 30% of the class sending me an email, oh, you gave us the wrong equation for the first law of thermodynamics. No, I didn't. Q gained, if we take Q lost to the other side, equal minus Q lost. So those two equations are the same. So most probably I will gonna give you this one, and then some of you gonna send me an email saying, oh, you gave me the wrong equation, and I'm not able to solve this. 30% every semester. No, it's exactly the same equation, guys. It's just they rearrange it, and they put the Q loss to the other side. In other words, it's saying the amount of energy in this equation right here, it's saying the amount of energy is the same, but one gained, the other lost, because we just said that the plus is gaining, minus is losing. So losing the energy, or the system lost the energy. So those two equations are the same, okay? If you see it on OWL the other way around, it's still the same equation, it's just they rearrange it on OWL. Okay, so, in your opinion, we said that the T final is something between 75 and 30 in the example before, and in your opinion, which one lost the energy and which one gained the energy? Let me go one. Which one lost energy and which one gained energy? Did the 75 lose energy? Very good. So definitely then, if the 75 lost some energy, definitely the 30 gained some energy. Always the heat gonna flow from the object which is more hot at higher temperature to the lower temperature. Always the heat flows, I think I wrote that. The heat flows from the object or substance of higher temperature to the one of lower temperature. Remember that thermal energy, which is heat, which is temperature, it's due to kinetics. It's due to the movement of those particles in there. So the one at higher temperature, it's at higher movement, it has more motion, and this is why always the heat flows from the object or the substance at high temperature to a low temperature. And this is why our T final is in between the two. It's not higher than one, it's not lower than the other. And definitely the heat gained equal plus the heat lost equal to 0. Okay, let's see how we're gonna use that. An example of that, how we're gonna do the calculation. So an 88 gram piece of iron, so I have an iron, and the mass of that iron is 88.5 grams, whose temperature, so T initial for iron, equals 78.8 degrees Celsius, is placed in a beaker. So we have a beaker, the beaker has water, I guess, and the mass of water equal to 244 grams. The T initial of water is 18.8 Celsius. When thermal equilibrium is reached, that means it's telling you we added this iron at 78 to the water, which is at 18. We waited until thermal equilibrium. What is the final temperature? So the way that we're gonna solve it, we know that Q gained equal minus Q lost. That's our equation, right? So Q gained, the one that gained energy is the water, equal minus Q lost, which is the iron. I know how to calculate Q. We learned that on Friday, that the Q is the mass of the water multiplied by the specific heat of the water, T final minus T initial of water, minus the mass of iron, the specific heat capacity of iron, T final minus T initial of the iron. Now, I know for sure that T final for both water and iron, T final water, iron, equal to T final water. Why? Because it's a thermal equilibrium. Both of them, they're gonna have the same temperature. And this is one of the mistakes that almost happens whenever you do you think that some of you think that there is two T finals. And they think it is one equation, two unknown, and they don't know how to solve it. Okay? The T final for both is gonna be the same. When we added both waters together, at the end we find one temperature. Now I'm gonna plug in the numbers, and I'm gonna make sure that I'm plugging the right number on the right side of the equation. The mass of the water is 244 grams. The specific heat capacity of the water is 4.184 joule gram Kelvin. T final is what I'm looking for. T initial of water is 18.8 Celsius, equal to minus the mass of the iron is 88.5 grams. Specific heat capacity of iron is 0.449 joule gram Kelvin. T final is what I'm looking for, and T initial of the iron is 78.8 Celsius. Now I just want to comment that again here I can put Celsius because both of them are, it's the difference between temperature. It's not, if it is temperature alone, no, it's wrong. But since it is delta T, I can put Celsius in there. My answer gonna be in Celsius, not in Kelvin. Now, do you know how to solve this equation? Okay? If you don't know how to solve one equation, one unknown, that's a prerequisite for this course. It's the basic algebra, how to solve this. If you don't know, I advise you either to go to a math tutor, figure it out, because you're gonna be in trouble in exam 2 if you don't know how to solve one equation, one unknown. If you don't wanna go to a math tutor, ask me, come to my office hours and ask me, I'll be happy to answer you. But if you don't know how to do that, you're gonna be in trouble in this chapter, guys. Okay, I'm gonna show you how to do that. So first we multiply those two numbers, and then we expand this whole thing. And okay, I think I have the numbers ready. So for the water, it is 120 T final minus 18.8 Celsius equal minus 88.5 times 0. So that's going to end up with 39.7 multiplied by T final minus 78.8 Celsius. So what you're going to do next is expand. Multiply this by that, this by that. Then take T final or T finals to the same side and all the other numbers to the other side. Make sure that when you move something from the right side to the left side of the equation, the plus is going to be minus, the minus is going to be plus. And the answer for this, after you do that, the T final gonna be, where did I put that? It's gonna be 16.37 Celsius. That's the answer. Which is not right. No. I think, because it should be, T final should be in between the two. Let me do the calculation really fast on. Or if somebody can do, okay, let me do the calculation really fast. Okay, you know what? I'm gonna do the calculation and send you the answer. Sorry, but I have the wrong calculation in here. Definitely T final should be somewhere between 78 and 18.8. I'm going to do the calculation and send it by email to everybody, but definitely whatever we did here, right here, is right, okay? So now, get the idea, guys? Cool. So let's do an eye clicker. Okay. I'm going to put it at 3 minutes. Don't rush. It means you need to do some calculation. Do you need some more time, guys? Than 3? Okay. Okay, so I'm going to stop it at 4:10. So, so the most popular answer is A. A is the right answer. Okay, so how are we gonna handle it? First of all, a lump of chromium. So we have chromium has a mass. The mass of chromium equal 92.5 grams. The temperature, the T initial of that lump is 89.5. It's placed in a beaker. The beaker volume, the water in the beaker is 75.2 milliliters. So we don't have grams, we have milliliters of water. At the T initial equal 20.5 Celsius. After stirring the T final, so T final for both equal 27.4 degrees, 27.4 degrees. What is the specific heat capacity of a chromium? Knowing that the density of water is 1 gram per milliliter. So first of all, this is kind of tell you a method that sometimes we use this thermal equilibrium to figure out the heat capacity of some elements that they are new or unknown, or even if you want to identify what is the element, you can do this kind of technique and from there calculate the specific heat capacity and then go to the tables and figure out what is that. Now, we know that Q lost equal minus Q gained. So the one that lost is clearly Q chromium, and the Q gained is water. Okay? Now the first thing that I have a volume, I don't have a mass for water. Yet I have the density, so I know that the density is the mass over the volume. Then I can calculate the mass knowing that it is the density times the volume. So it is 1 gram per milliliter multiplied by 75.2 milliliter. So since the density of water is 1, the mass equal to the volume. So now I know I have 75.2 grams of water. So now the mass of chromium, so I know that the mass of chromium is 92.5 grams. I'm looking for the specific heat capacity of the chromium. T final minus T initial, it's 27.4 minus 89.5 equal to minus the mass of water I just calculated is 75.2 grams. Specific heat capacity of water is 4.14 joule gram Kelvin, 84 joule gram Kelvin. T final minus T initial 27.4 minus 20.5. So the specific, if you do this, one equation, one unknown, is the answer. Okay? Is the right answer. Okay. So practice more. The more you practice, the better you get in this. This question can be asked in like 100 ways. One time about T final, one time about T initial, one time. It's all the time you're gonna have everything you're asked about one of the variable, either the specific heat capacity or the mass or the temperature, T initial, T final. There is hundreds of ways that we can ask exactly the same question, which is about thermal equilibrium. Now, before we go any further, we have to identify two terms. So whenever I'm talking about system, I mean the object or set of objects that is studied. Whenever I'm talking about the surrounding, it's everything else. So in the example of water that we heated it up, the water that we heat up, a beaker with water and we heat the water up. The system is the water. Anything else is the surrounding. So the system is what we're studying, whether it is a reaction, whether it is water we're heating, ice we're melting, water we're evaporating, anything, that's the system. But anything else is the surrounding. So in other words, if I have water in this beaker and I'm heating up, the system is the water. This room is the surrounding. The beaker is the surrounding. Anything else around the water is the surrounding. The only thing that is the system is the water that I'm heating. Now we have three kinds of systems that we're going to talk about in this chapter, and you need to know the difference between the three. The first one is the open system. An open system is like me having water in this beaker. Okay? So this is a system, and it is called open because I can add water. I can add more water to it, and I can add energy or take energy from the system. This is why it is called a matter. It is called an open system. It is called an open system because I can add either water. Anytime I want, I can increase the mass of water or decrease it, and I can add energy or take energy. So an open system is a system that we can add or take either matter or material and energy. Both. We can add to the system both energy and material, or take. We can either take or give the system. Now, let's say the other system is something like this. Okay? A closed system it is closed. I can't add matter to it because by definition it's a closed system that I can't add water to it yet, or material to it, or matter to it, yet I can increase the temperature, or for example heat it up, or take energy from it, cool it down, or heat it up. So a closed system is a system that can exchange energy, but not material or matter. Okay? Now the isolated system is a system that you can't add to it anything, so it is closed and it is isolated. In other words, for example, the coffee, let's say your coffee cup or thermostat that you use for your coffee, let's say it is sealed and you can't open it, you can't drink coffee from it. It's isolated system. Why? Because you can't decrease or increase the matter, the coffee which is inside, and it is isolated. That means the heat wouldn't be lost, because this is the idea of a thermostat, that the coffee will stay at the same temperature because it doesn't lose heat to the surrounding. And probably by Friday, we're going to show you those two systems, the calorimeter, both calorimeters, the bomb calorimeter, and the calorimeter. So the isolated system, it does not exchange, no exchange for matter or energy. Okay? So you need to know those. As we're going to talk about those three systems. I'm going to say, oh, this is an isolated system. So you should know directly that, oh, there is no exchange of heat, no matter outside, but to the outside they don't lose or gain energy. Exchange, the closed one is the one that you can either increase heat, take heat from the system, but you cannot add matter, and the open system is the system that you can add. So for example, we'll talk about the different examples as we go. So those are the three definitions of the systems. Now we're going to talk about energy and the changes of state. In all what I talked about before, I said that I have water, I'm heating the water up, but it stayed in the liquid state, right? I didn't say the liquid evaporated, I didn't say the water melted, for example, the ice melted. So in all of the examples that we talked about before, we didn't change the state. The state was the same. And this is why we were allowed to use Q equal mass specific heat capacity delta T. That applies when you're still in the same phase. For example, you started with a liquid and you ended up with a liquid. An example of that, heating the water from 20 to 90, not more than that. For example, not to the gas phase. Or for example, heating metal, for example, for 20 degrees, it didn't melt. today what we're going to talk about now is what if I want to take ice and melt it to water? How I'm going to do that? Can I use the same equation, which is Q equal mass times specific heat capacity delta T, to calculate how much energy I need to take ice to water? So this is what we're going to learn in a minute. So as you know, definitely there are 3 states of matter: solid, liquid, and gas. Almost every matter out there or material out there can have solid and liquid and gas. There are some exceptions we're not going to talk about in this course. So now to go from, as we said before in chapter 1, that to go from solid to liquid to gas, we need higher temperature. And the reason behind it, because I want those particles which are in the solid close to each other to be far away from each other. So I need heat to do so, which is temperature. The liquid also can go to the gas, so the particles will be farther away from each other. So this also needs energy. Now, when we go from solid to liquid, and an example of that which is going from ice to liquid, there is a certain energy that we need, which is called the delta H of fusion, or heat of fusion. We call the energy that we need to take something from solid to liquid the heat of fusion. And to take something from solid to liquid, that means you need energy. So the energy is positive. Why? Because the system needs energy to do that. Okay? Usually the heat of fusion is represented in joule per gram, and it is the energy needed to transfer a solid to liquid. Usually solid go to liquid not at any temperature. For example, if I have ice at minus 50, it wouldn't go to liquid until we get it to the melting point, which is 0 degrees. Things melt at their melting point. They can't melt at minus 50 and their melting point is 0. Anything only melts at its melting point. So if it is lower than its melting points, first you have to heat it in the phase that it is to get to the melting point, then things melt. So delta heat, the delta H of fusion, this is how you're going to see it. This is for 1 gram because it's a joule per gram. So usually the values of delta H of fusion is tabulated. That means you find it on tables. On OWL, you go hit the tables, you find the delta H fusion for every matter out there, and it's going to be in a joule per gram. Okay? That means it depends on the mass. And it is positive. That means you need energy to get something from solid to liquid. Now, the energy that you need to take a liquid to solid, that means freeze the water, for example. That's you take energy from the system. It is minus delta H fusion. So it's going to be negative, not positive. Why? Because you take energy from the water to change it from liquid to solid. Okay, so keep that in mind. If you wanted to change something from solid to liquid, it is positive energy. You're going to give the system that energy. The system needs this energy. While if you want to take it from liquid to solid, no, you're going to take from the system energy. So this is delta H of fusion. Now to go from liquid to gas, we call this, there is a heat for that, and we call this the delta H of vaporization. Also, it is tabulated values. You can find it in OWL. And sometimes it's a joule per mole, and this is confusing for some of you. Sometimes it's a joule per mole, sometimes it's a joule per gram. It depends what the table represented. You have to get used to both ideas. It could be joule per mole or a joule per gram, and we're going to talk about what's the difference between the two. So, to take something from liquid to gas, you need energy. The system needs energy, so delta H of vaporization is positive. To condense something, take it from gas to liquid, which is condensation. The energy is negative, minus delta H of vaporization, because now you're going to take energy from the system to take it from the gas to the liquid. And again, you can't evaporate. You can only evaporate something at its boiling point. You can't evaporate, for example, water at 20 degrees. You need to take water to 100, And at what 100, if you give it more energy or enough energy, it's going to evaporate. Water does not evaporate, for example, at minus 50 or something. You need to take the thing to its boiling point. And I'm keep repeating this because each semester we're going to get to a confusion in a minute where some of you think, oh, I can melt things, why not at minus 50? Okay, or at a 20. Now to take something, okay, we talked about this, the minus and the plus, so we're going to keep going. Now, the energy that we need to melt something, for example, if I want to melt a 1 gram of ice, is it the same energy that I need to melt 200 grams of ice? Is it the same energy? Would it be the same energy? No. And this is why Q melting is the mass, because it depends on the mass, how much I'm heating, how much I'm melting. The mass times the delta A, the heat of a fusion. So Q melting, if the material is at its melting point, the energy that I need to take it from ice to liquid at its melting point is M times the delta H of fusion. It's going from solid to liquid. I said to gas and that's wrong. Okay? Here it's the melting, we're going from solid to liquid. The melting time delta H of fusion is a joule per gram. Okay? So if it is at its melting point, the Q melting, how much energy I need to melt something at its melting point is M times delta H of a fusion. Now, if I wanted to go from liquid to solid, Q solidification, which is going from liquid to solid, solidification, equal minus M delta H of a fusion. Okay? This is if we want to go from solid to liquid, from liquid to solid. Now, if I have a liquid and I want to change it to gas, first it must be at its boiling point. The energy that I need to take it from liquid to gas is Q vaporization, is M times the delta heat of vaporization, and that should be in grams. So, Q of vaporization is M times the heat of vaporization joule per gram. So if you look into the table and you have the delta H of vaporization in joule per gram, you're going to multiply by the mass. If you open the tables and you find the delta H of vaporization joule per mole, you're going to multiply the delta heat of vaporization by number of moles. So you have to be aware of the difference between the two. Sometimes you will be given in exam the delta H of vaporization in a joule per gram, sometimes in a joule per mole. So you have to be aware to both of them. So see you tomorrow at 7 p.m. and we're going to keep going with that on Friday. Let's tear